Yes. Good evening, all of you. See the question. Read the question first. An 8-pole lap-wound DC generator has 60 slots. The number of slots are 60 with 22 conductors per slot. Then total conductors, how much? Total conductors Z equals to 60 slots, each slot having 22 conductors. So this is the total conductors. Calculate. Z equal to 1320 conductors. Okay, Z it is total conductors. Now the ratio of pole arc to pole pitch. So there is one ratio, pole arc to pole pitch ratio given. How much it is? 0.64. Okay. The diameter of the bore of the pole shoe is 0.6 meters. See what is that bore of the pole shoe is. Let this is that there are 4 poles. For example, I'm taking 4 poles. 8 poles are there. This generator 8 poles, but example I'm taking 4 poles. Okay, 4 pole generator. North, south, north, south. 4 poles. See here. The diameter of bore of the pole shoe. What is the meaning of this is this one. The diameter of bore of the pole shoe, nothing but this one. Bore means let us join the arc of all the poles. Join the arc of all the poles. It forms like a cylindrical shape only approximately. Okay, like that. Join the pole arc of all the poles. This is called bore of the pole shoe. This is called bore of pole shoe, and this diameter is how much? This diameter is given as 0.6 meters. This is 0.6 meters. Okay, this is the meaning. Bore of the pole shoe is if you join the pole arc of all the poles, it forms like a circular shape. That is called bore of the pole shoe. Okay, and given pole arc to pole pitch ratio. Pole arc is only this. Only this is pole arc. This is only pole arc. Okay, pole pitch is what? If you take from center shaft, this is pole pitch or not? This is pole pitch. Pole pitch means 180 degrees electrical. This is the pole pitch. This is the pole arc. Pole pitch is this much, 180 degrees. Pole arc is this much. Pole arc to pole pitch ratio given as 0.64. Pole arc to pole pitch ratio given 0.64. The length of the pole shoe, length of the pole shoe is given 0.6 meters. Length is how much? 0.3 meters. Length is 0.3 meters. Length of the pole shoe is 0.3. The air gap flux density B equals to 0.25 Weber per meter square. Okay, the generator EMF is 400 volts. Generator EMF EG is 400 volts. What we have to find? Speed of the generator we need to calculate in the question. So EMF equation you have to use finally. What is the EMF equation? E equals to Z phi N P by 68. Okay, Z phi N P by 68. In that every value they given, only unknown in this equation is speed of the generator N, that is EG into 68 divided by Z phi P. So EG is there, EMF given, and number of parallel paths as it is lab connected, A equal to P, 8 poles are there, and only unknown Z also we calculated 1320. Only unknown in this equation is phi. That phi we have to calculate in this question mainly. What is phi? Flux. What is flux per pole? In terms of flux density B into A. Flux density into area of that cross section. Area of which cross section? This total bore. This total, whatever the bore of the pole we have drawn, this total surface area you have to find. Total area. What is the area of that surface of cylindrical? Surface area of cylinder formula is what? The area of surface area of cylinder is, what is that? See, what is the perimeter of the circle? Perimeter of circle, 2 pi r. 2 pi r perimeter. And if you multiply perimeter with length, you will get the total surface area. 2 pi r is the perimeter, this one. This circle perimeter or circumference of the circle. Perimeter or circumference is 2 pi r. 2 pi r radius of the bore of the pole shoe, radius. Diameter is there, radius is half of that, 0.3. And if you multiply with length of the pole shoe, actually length of the bore is nothing but length of the pole shoe only. Whatever the length of pole shoe is there, same length bore also will be there. And if you multiply, you will get. Generally we write this is in terms of pi dl. We write this area as pi dl. Remember this. We write the area is pi dl. D is diameter, 2r into L, length of the bore of the pole shoe, or length of the pole shoe also enough. Okay, that is the L. Now if you substitute here B into A, you will get flux per pole. Then substitute in this equation, you will get the speed of generator. But here, if you find area, you will get total area, total surface area you will get. But how much pole shoe is covered? Pole shoe is not covering total, no. Pole pitch is 180 degrees, but how much pole shoe is covering? Only small angle. That angle they given, percentage they given 0.64. Means you have to multiply here the total area with this pole arc to pole pitch ratio. Pole arc to pole pitch ratio. Then you get flux per pole. Clear? If you find area, you will get total area there. But poles are not covering total area. Poles are covering only up to pole arc. So pole arc is how much? 0.64 times of pole pitch. So that we have to multiply. Then you will get flux per pole. Okay. So this is total flux. Per pole means again divided by P you have to take. Okay. Flux per pole. In the equation, whatever phi is there, that is flux per pole. That's why you have to multiply with this per pole. This is total flux. Area of total you will get with respect to pole arc by pole pitch, and again divided with poles. Flux per pole. First, see here. Flux equals to B into A into pole arc to pole pitch. Pole arc to pole pitch. So this value will give for total poles, but we need per pole. Therefore, flux per pole is phi equals to B into A divided by number of poles into pole arc to pole pitch. This is only you have to know. That's it. And what is the B value given? B is given here, 0.25 Weber per meter square. 0.25. And what is area? Pi dl. Pi into diameter. What is the diameter given? Diameter is how much? 0.6 meters. 0.6. L. Length of the pole shoe how much? 0.3 meters. 0.3 divided by how many poles are there total? 8 poles. 8 poles in the question, but I taken here 4 just to show it. Okay, don't confuse in that. Into pole arc to pole pitch ratio is 0.64. So solve this value, you will get flux per pole 5. How much it is? Tell me. Flux per pole is how much? 0.0113, right? 0.0113 Webers. This is the flux per pole. Okay. Once you find this enough, you will get the answer. Only 5 unknown in this. Therefore, substitute in the EMF equation. No? So all of you got this 0.0113 Webers. Okay, right. So why we are multiplying this ratio? If you find only phi equal to BA divided by P, what is that flux? This is the flux for total 180 degrees you will get. Divided by poles, if you write, one pole is how much? 180 degrees. But how much flux distribution is there? Whatever the pole arc is there, up to that only flux will distribute uniformly. After that, flux value decreases. That flux will not be there. That's why we are multiplying with pole arc to pole pitch. So whenever they don't give this relation, then we take only this only, phi equal to BA by P. B into A by P only. When they don't give this relation. If it is given, we have to multiply with this ratio. Otherwise, neglect this. Okay. So flux value is this. Therefore, the speed N equal to, what is the speed equation? This is Eg into 60A by Z5P. Eg into 60A divided by Z5P. Substitute all the values here. The speed equal to Eg how much? Eg 400 volts. 60 lap wound it is. That's why number of poles, number of parallel paths equal to number of poles 8 divided by Z value 1320. Z value 1320 only. Yes, 1320. Next, flux per pole is 0.0113 into number of poles are 8. Calculate the speed of generator here. What is the answer? Speed 16. No, Sunil, check once. 0.0113 only we get. Check again your values. 1609 RPM. Okay, right. 1609, approximately 1610 RPM is the answer. Okay, 1610 RPM. There is some model, another question here, that is, they don't give bore of the pole shoe. They will give armature only. Armature. They don't give the diameter of bore of the pole shoe. Irrespective of that diameter of bore of the pole shoe, they will give diameter of armature only. They will give armature diameter. So you have to consider that is itself. That is itself the area of the diameter or bore of the pole shoe, almost same, because small gaps will be there. That's why whenever they give an armature diameter also, you can proceed the same equation. Armature diameter also, when they given, proceed same as it is. Okay. In some of the questions, they give directly bore of the pole shoe, or they will give sometimes only armature diameter. Okay. There is some distance between the poles and armature, some small gap will be there, like 5 mm, 8 mm. Okay. Based on the type of DC machine, whether it is large size or small size. Even if they given diameter of armature, use the same relations, approximately same it is. Okay, so area, how we are calculating area? This is what area. How to find that area? First calculate the front side, the total perimeter of this surface area only we are calculating now. See this perimeter or circumference of the circle. If you see, this is let like armature, it is rotor. So we are finding now this circumference first. This circumference of the circle. What is circumference of the circle? 2 pi r. 2 pi r. Perimeter or circumference. Now what is the length of this? How much length is there? That length also they given. Now if you multiply that perimeter with length, you will get total surface area. No? 2 pi r into length. 2 pi r nothing but pi d. D is diameter 2r into length of that L, pi dl. That is total surface area we get. Okay, got it now? Okay, so let's continue our actual discussion. So in the last class, we have seen separately excited DC machine, separately excited generator and motor in that. Now let's see self-excited DC machine. See, this is not area of air gap. The area, whatever that loop we are drawing now, surface area only, not complete area that is. That is not complete. That is not volume of the rotor. No, only surface area we are calculating. Surface. Okay, don't confuse in that. That is including air gap only. Including air gap, because if you draw the total pole arc, if you join, so here itself we have rotor. Rotor is there here. Rotor is here. This is rotor. Okay, you are drawing this connection, that is pole arc of all the poles you are connecting just. It is like a circular form. And this diameter we call, this is called bore of the pole shoe. This circle we call bore of the pole shoe, that is bore. Inside there is armature and there is some gap also here, air gap that is. Okay. Flux per pole means we need to calculate only for one pole. But whatever the formula, if you don't divide with poles, that will give for all poles. That's why we are dividing with the total poles, so that one pole flux we get. Okay. See, in the figure, I taken 4 poles just to show what is bore of the pole shoe. But in the question, how many poles are there? 8. That's why I taken 8 here. Clear? Figure and question is different. Figure I taken 4 because 8 poles we cannot run. Okay, next, self-excited DC machine. Second one, self-excited DC machine. Separately we have completed yesterday. Now self-excited DC machine. In self-excited again, there are mainly 3 types: DC shunt, DC series, DC compound. Let us see first DC shunt machine. DC shunt machine. Now here also we will see both simultaneously, generator, motor, KVL equations. First, generator. Take the figure, generator figure. let two pole DC shunt generator it is. See, first of all, in self-excited DC machines, what is the meaning self means? Self-excited means in these machines, we don't have any separate voltage source for field winding. Like in previous separately excited machine, field winding, we are giving a voltage, DC voltage. To the field winding, we are giving DC voltage to create the required flux. But here we don't give any separate voltage. External voltage we don't give. What is the output of DC generator? DC voltage. That is itself we give back to field winding to create the required flux. How we connected, how we are giving, how we are exciting the field winding. If it is parallelly excited, shunt. If it is series excited, series machine. Okay, only the connection will change, parallel or series. So in self-excited DC machine, the field is excited from armature itself. The field is excited from armature. The field is excited from armature. Okay, see the figure for shunt machine. This is the field winding. On the pole core, field winding, and armature winding it is. So the supply to the field winding is from armature only. By connecting it is in parallel. See, field winding I am connecting to the armature in parallel. Field winding is connecting in parallel with armature. That's it. So this is a shunt generator. This is shunt generator. Field is excited from armature by connecting in parallel. Okay. So this is direct machine representation. Now let's see the equivalent circuit of shunt machine. This is the field winding. And here one interesting thing is, see, armature, field winding, both are in parallel. See, first of all, in this shunt field winding connected parallelly with armature. Now the current in this field winding is let ISH, field current, shunt field current, resistance of the field winding RSH. Now first, how to represent shunt field winding? Representation. More number of turns. Shunt field winding should have more number of turns. Okay, more turns. And it is made up of thick wire or thin wire? It should be made up of thin wire. It should be made up of thin wire. Now tell me here, why it should have more turns? Why it should be made up of thin wire? That we should know first. Otherwise, shunt machine you can draw directly, shunt generator or shunt motor. But main thing is why it is required more turns and thin wire. So still, I can say during our engineering, so no one will give all these informations in the lab also. So what is the lab purpose? After going to lab, we should know practically something. Whatever you learn theoretically, you need to prove that in practicals. But we are not proving anything. We are going to labs regularly in our engineering, writing observations and record carefully and in time, because marks will reduce in the externals. Only that fear is there. And we don't have any fear that as we are anything learning practically or not. That we never think of. But anyhow, That is common in everywhere, every engineering colleges, mostly private colleges. Okay, but why it should have more number of turns? First, let us see, as we are connecting in parallel, no, it is, what should be the resistance of shunt field winding? More resistance or less resistance? It is a load. Across the load, the voltage is always terminal voltage, and EMF induced in generator we call EG. First write the equations. This is the current IA and load current IL. So what is the main purpose of generator? To supply loads. Main purpose of generator is to supply loads, but not field winding. No, field winding is not the main purpose of generator. Main purpose is load, to supply to the loads. So in order to supply most of the current to the load, what should be the field current? Less. How can we get less amount of field current? Let us keep the high resistance in this. Keep the shunt field resistance very high so that field current is reduced and most of the current will go to load only. Okay, most of the current will go to load only. For that, as we required high resistance means what should be the thickness of wire? We know resistance R equal to rho L by A. Rho L by A. If area of cross section is less, your resistance will be high. Less cross sectional area means thin wire or not? Yes. Less cross section is thin wire. Okay, wire is thin because we need high resistance. That is all. Then why we have more turns here? Why we should take more turns? Yes, we need to take more turns because flux is proportional to MMF. That MMF is proportional to number of turns in the winding and current in the winding. Okay, already you are creating a very small field current by having high resistance in this. If current is very less, then how the required flux will produce? Then MMF is not sufficient. For that reason, we will increase number of turns so that the required flux can produce. Clear? That's why the shunt field is always represented with more number of turns and it is made up of thin wire. Thin wire because of high resistance required. Otherwise, if resistance is low, then most of the current will come to load on this resistance on field winding on, and load current will reduce. Okay. So now observe. So whenever we rotate, an EMF will induce. This is EG. This is armature current. In that, some current will go to the field winding as field current. Now, when there is a current, flux will produce EMF induce. This is our load current, terminal voltage. But in self-excited generators, there are some conditions. If that conditions are satisfied, then only voltage builds up. Otherwise, no voltage. Why? Because you think here. Observe this second diagram. When there is no voltage here, is there any field current here? No field current, zero. If field current zero, what is the flux? Zero. Then how EMF induce? Assume that field current zero initially. Field current zero. If field current zero, whenever you rotate, is any voltage will induce here? No voltage because no field current, no flux in generator. In order to produce EMF in generators, mainly two things are required: speed and flux. Speed should be there, flux also should be there. If any one is zero out of this, no EMF will come. But in separately excited generators, observe, you are giving a separate voltage source to field winding, field current will flow, flux will generate. When you rotate, EMF will induce. But that is not possible in self-excited generators, shunt, series, compound. In all these, the voltage cannot be built up if there is no flux. That's why there are some conditions here only for self-excited generators. If that conditions are satisfied, then only voltage will build up. Okay. So anyhow, we will see that voltage conditions for voltage build up in the after completion of shunt. First, complete this. Write one statement here. Write one statement. In shunt machine, that is valid for both generator and motor. In shunt machine, the field is excited from armature by connecting in parallel by connecting in parallel hence it should have high resistance. It should have high resistance comma it is made up of thin wire and more number of turns to produce the required flux. To produce the required flux. Okay. Now, if you write KVL of generator, how we get KVL in this supply? EMF induced in generator is EG, and the output voltage we are getting V, terminal voltage at load across the loads. So if you apply KVL, EG equals to V output voltage plus drops in this. What are the drops? Common. Drops are common. IARA drop plus brush drop. Okay. Now from this figure, what is the IA? IA. Apply KCL at the node. Incoming current equal to sum of outgoing currents. IA equal to IL plus ISH. And what is ISH in this? What is this node voltage? EG or V? This node voltage is V, because this point, all are same or not? That is V only. Same point extended just. So it is V, not EG. EG is inside the armature, that is. Once outside the brush, whatever is coming, that is V only. That's why ISH is V by RSH. Field current is V by RSH. Okay, so remember these equations. It is for generator. Now, if it is motor, IL will reverse, IA will reverse. Then write the equation for motor. Next, motor. Motor. If it is motor, let us draw only second figure enough. Second figure. So motor means we need to give supply voltage plus minus. Now it will draw a current IL, IA, ISH, and armature resistance RA. Let it is motor speed NM. Now in motor, whatever EMF induced, what we call that? Back EMF. Every motor same. The EMF induced in motor is back EMF. Now input voltage is V here, and we are getting some output voltage in the armature EB. So the KVL equation is V equals to EB plus drops, IARA drop plus brush drop. Same, just these two will interchange. Drops remain same, generator and motor. And at the node, same voltage V appeared. What is ISH? V by RSH. And if you apply KCL, IL equal to IA plus ISH. If you want IA, IL minus ISH. Okay, remember these equations. What is the field current of shunt motor? Always constant or not? Yes, always constant. Why? Supply voltage constant, resistance constant. So ISH constant. When ISH constant, what is the flux in motor? Also constant. That's why the DC shunt motor is also a constant flux device. Separately excited, flux constant only. Like the DC shunt motor also a constant flux device. So what are the constant flux devices? DC shunt motor, approximately separately excited motor, and transformer and induction motor also constant flux, just like transformer principle. Okay, but variable device is series motor, that is variable flux motor. Okay, so this is about generator and motor of shunt machine. Let's see some questions on this shunt. Then we go to conditions to build up voltage. Generator means we are rotating mechanical input. How EMF induced, that we will see later. Okay. Initial rotations means motor, DC motor. See, motor not required. When we give supply voltage, no, field current is there, armature current also, both are there. Now DC motor is self-start. No conditions for motors. Conditions is only for generator required, not for motors. Okay. Yes, wait for some time, that we will see. DC motors are self-started. Okay, self-started. Self-started only. DC motors are self-started. Self-start motor it is. How it is self-start, I will show you in armature reaction. Armature reaction, very important. If anybody miss also now, don't miss armature reaction. Mostly by tomorrow only we start armature reaction. Okay. Okay. See the questions on this. See this question. A 120 volt wave connected DC shunt generator supplying a lighting load of supplying a lighting load of 50 lamps, each of 60 watts. Each lamp power is 60 watts. The field resistance is 60 ohms. Then calculate the current in each armature conductor. Current in each armature conductor. Okay, try this first. So 2 minutes time, try it first. Try this. First draw the figure, a 120 volt wave connected DC shunt generator. So draw the shunt generator figure. Loads always connecting in parallel only, no? Loads means connected in parallel. So there is a shunt generator. It is supplying a lighting load. Lighting load of 50 lamps. Total how many lamps are there? 50 lamps are there. All 50 lamps are parallelly connected. Let lamp 1, lamp 2, L1, L2, like that. There are total 50 lamps here. L50. Okay, 50 lamps are there. Each lamp capacity how much? 60 watts. Given that the field resistance is 60 ohms, And as it is wave connected, how many parallel paths are there in wave connection? Two parallel paths. This is armature current, load current, field current. 120 volts means this is terminal voltage. Always the voltage rating given in generators is terminal voltages or full load voltages. We have to find the current in each armature conductor. Yes, yes, very good. Most of you given right. 13.5 amperes. 13.5 is correct. See, across the lamp, power rating is there, voltage is there. Same voltage will appear for all the lamps now, parallel. So, what is the current drawn by each lamp? IL1, calculate. Power. Power is there 60, voltage is there 120. And what is the current drawn by each lamp? Light, 0.5 amperes. So each lamp is drawing a current of 0.5 amperes. So all lamps are same 0.5. Then what is the total load current? 50 lamps are there total. So 50 into 0.5. That is 25 amperes is the load current. Then what is ISH? V by RSH. V is 120. RSH is 60. 120 by 60, 2 amperes. Then what is IA? IL plus ISH. 25 plus 2, 27. This is IA. But question is what? Not armature current. The current in each armature conductor. So previously in lap winding I given current in one conductor, nothing but current in parallel path. Both are same. Current in each armature conductor is nothing but current in each parallel path. Current in each parallel path. Both are same. So how many parallel paths are there? 2. 27 is total current. So equally divides 13.5, 13.5. So answer is 13.5 amperes. Therefore, current in each armature conductor armature conductor is equal to 13.5 amperes. Okay, right, all of you given right. Okay, next question. Next, completed all of you this. 13.5, because it is sum is no. What is IA? IL plus ISH. IL plus ISH. ISH 2. IL is 25. 25 plus 2, 27. That's why. Okay. Anku. See, in your batch, it is good. So most of the people will give response immediately. But in some batches, we have to keep on asking completed or understanding like this. Generally in online class, what is in online, we have to continuously ask, make some response. Otherwise, we cannot. Difficult for us. Generally in offline class, what exactly opposite? In offline class, you should not make any noise, but in online you should make noise. Okay, next question. Say this question. A 250 volt DC shunt machine has armature resistance 0.6 ohm, field resistance 125 ohms. The machine is connected to 250 volt supply. That is voltage is 250 volts. The motor, this is not motor, machine. The machine is operated as a generator and then as a motor separately. Same machine you can operate as generator and also you can operate as motor. Okay. The line current in both cases is 50 amperes. Now you have to find the ratio of speed as generator to the speed as motor. This ratio you need to calculate. This ratio. Same model in gate 21 also. On shunt machine only, same model. First draw the figure. Initially the machine operating as generator. It is operating as generator. Shunt generator. Just calculating EMF in both cases, generator and motor. That's it. So in case of generator, what is the terminal voltage? 250. Generator or motor, terminal voltage is 250 only. What is the line current in both cases given? 50 amperes. Line current or load current 50. And RSH is 125. So ISH is what? 250 by 125. V by RSH. ISH will be 2 amperes. Then what is IA? Sum of the two. 50 plus 2 is 52 amperes. Then calculate EG in generator. Calculate EG by applying KVL. What is the KVL? V plus IA RA. Brush drop is not given, so neglect that. What is V 250 plus IA is 52, RA is 0.6. What is EG? 282, something like 281.2, right? Yes, 281.2. So answer also given some people 1.27, right? Very good. 1.27 is correct. Yes, 1.27, right? Okay, this is generator case. Now same machine operating as motor. Again take the figure. Same machine operating as a motor. Line current also same in motor, 50 only. Supply is 250. Line current. Now it will take the current 50. RSH is same 125. That's why ISH will not change 2 amperes. Now what is IA? IA 50 minus 2, 48 amperes. In motor, whatever EMF induced, that is called EB. This is motor speed NM. Calculate back EMF, apply KVL again. KVL, EB equals to V minus IARA. 250 minus 48 into RA is 0.6. What is EB? EB how much? 221.2, right? 221.2. Okay, now apply the relation. We need the speed as generator to the ratio of generator speed to motor speed. We know N proportional to E by 5, just like previous yesterday's question. Ng by Nm equals to Eg by Eb into 5m by 5g. What is the flux in both cases? Constant, because field current is same only, not 2 ampere, 2 ampere. Flux is same, that's why I cancel that. Now the ratio Eg how much? 281.2. EB how much? 221.2. EB 221.2. Then calculate, you will get 1.27. This is the ratio of generator speed to motor speed. Okay. Okay, good. Next, starting conditions to build up voltage in self-excited generator. Right now, conditions to build up voltage. See, listen carefully these conditions, because after conditions I will give some questions. That questions you should answer. But still there is so much confusions in the questions. Let's see, are you able to answer the questions or not? Conditions to build up voltage in self-excited generators. Self-excited generators. Self-excited means all shunt series compound. Self-excited generators. So listen carefully, easily you can answer after understanding these conditions. Yes, line current or load current, both are same. Pratik, you said right. Yes, very good. Your way is right. That is, some people will give the answers quickly, means they are repeaters, as you said. Maybe all are not repeaters. They are did, maybe somebody may did. Okay. Anyhow, no problem. Which slide? Slide number 8F. This is only, no? See, all of you completed this. Okay, next. Let's see. See, write the condition first. See, the first and the most important conditions to build up voltage in self-excited generators is residual flux or residual magnetism. So in these generators, whatever the poles we are using, the poles should have the property of retentivity. Due to that retentivity, they will hold some flux lines. That flux we call residual flux. So this must be there. Even there is no field current, there must be some flux in the poles. That is called residual flux. And this residual flux is due to the property of retentivity of material. Retent means hold. So generally, what is the electromagnet nature? So if you take an electromagnet, how it behaves? See, electromagnet it is. Based on the current or excitation, flux will be there. So let us suppose supply given, current is flowing. When there is a current, according to right hand thumb rule, flux will produce. Let us consider the flux is in this direction. Flux lines is there like this. Flux, north pole, south pole. Let us remove the supply. What is the current now? 0. Whenever current 0, what should be the flux? Generally 0. So whenever current 0, immediately flux also 0. Then this type of magnets we should not prefer in self-excited generators. So they don't have any retentivity property. This material is not having any retentivity. That's why we have to choose a good ferromagnetic material, so that even current is 0, immediately flux is not 0. There is a small amount of flux still present, a small amount of flux in this. This flux we call residual flux. And this flux is due to the property of retentivity of the material. Because of that, it will hold some lines. Even field current is 0 in the coil or winding, there will be some flux. That is called residual flux. Okay, so write the statement first. Then we will see the figure how voltage builds up. Write the statement first. There must be a small amount of flux, always present in the generator, always present in the generator, in the generators, called residual flux, residual flux, which is due to the property of retentivity, property of retentivity, due to the property of retentivity. Okay, now let's see how voltage will build step by step because of residual flux. Now take these two figures with neat diagrams, little big one, so that you have to understand if you see after 20 days also. Take big figures. So I'm taking a two-pole generator, two-pole shunt generator. So shunt generator it is. Now observe, rotating in clockwise direction, assume clockwise direction rotating, and simultaneously take the side by this figure also, so that clarity will come how EMF induced. It is open circuited. Okay, load is not connected, open circuit. Now we are considering how EMF builds up in this condition. Observe now, all of you drawn. See, retentivity means that is the nature of the material. So need of retentivity means its nature. Retent means it will hold. If there is no retentivity to the material, it cannot hold. That is nature of the material. That is one property of the material. Yes, all should have that property. So here no hysteresis because the flux is DC, not variable flux. No, BH curve is different. This is different because BH is due to reversal of magnetization. Here there is no reversal, only one direction of flux only. Okay, see here. See, there is no field current here first. No field current in this. Okay, no field current. Observe this is also no EMF is there. Assume that still it is not rotated. No EMF, no field current in this. When there is EMF, then only a current will flow in this. Okay, so simultaneously I will draw OCC also. OCC also I am drawing. Open circuit characteristics. It is drawn between EMF versus field current, ISH. Tell me what is the field current now here? 0. Because no current, no voltage initially. That's why field current is 0. Whenever field current 0, now start the generator. Rotate the generator with the prime mover at some speed n in clockwise. Now once you start rotating, There is an armature winding in the rotor. Once you start rotating, some EMF will induce or not? Yes, a small amount of EMF, let EG1. Small amount, some 5 volts, 6 volts, 7 volts, like that. Small voltage, because EG proportional to, from EMF equation, speed and flux. How much flux is there initially? Residual. So this residual flux is generally 5 to 10% of rated flux or total flux. Very, very small, that is 5 to 10%. Now, due to that small amount of flux, once you start rotating, how much EMF induced? Small voltage, let that is EG1. Now, there is a small EMF EG1 of 10 volts. Small 10 volts is there. So, if you represent here, field current 0, still at that time, if you rotate, small amount of EMF induced. This is EG1. Okay, EG1. Now, when there is a voltage, there is a path for current or not? Closed path available through field winding, parallelly connected. That's why a small amount of current ISH1 will flow. A small current. Now observe the first figure also. Due to that, a small current ISH1. So first of all, I have to consider residual flux. So I'm considering residual flux is passing like this. Okay, initially residual flux is passing in this direction, upward. Now whenever field current is flowing, ISH1, now current is flowing in this direction, field winding. This is the path of current in field winding. Now due to the field winding, field current, observe the current direction. Apply your right hand thumb rule there. Whatever field current is flowing, it will produce an additional flux. Now that flux also coming in the same direction of residual. This is phi1. Okay. Already residual flux is there. Due to that, when you rotate, EMF induced. Already there is residual flux. Once we rotate, an EMF induced EG1, which causes again a field current ISH1. Due to that, additional flux is produced phi1. Now, what is the total flux in the generator here? Increase. Resultant flux increases. Whenever resultant flux increase, what is the EMF also? Increases. EMF depends on two things, speed and flux. Speed is same, but flux is increased. So your EMF also now increases. Let it is EG2. If you represent in OCC, observe EG1 initially, due to that a small current ISH1. ISH1. Due to that ISH1, total flux in the generator increases, then overall EMF also increases. EG2 it is. Okay, EMF increase, EG2. Now EG1 increases to EG2. As voltage increase, again what is the magnitude of current? ISH2. Again field current increase. Again flux increase. Again overall flux increases. Again EMF increases. This process will continue. Up to what it will continue? Saturation of poles. Up to saturation it will continue. Flux increase, EMF increase, flux increase, EMF increase, and so on, continuously increases up to saturation point. Once the poles are saturated, flux become constant. Once flux is constant, your EMF also constant, or voltage of generator fixed. After that it won't change. Almost constant voltage it will show. And if you represent here, see EG1, EG2, again ISH2 due to that, and again overall flux increase, again EMF increase, like that it will build, the voltage will build continuously. The voltage builds up continuously. Up to what it will build continuously? Saturation. Assume that saturation takes place here. Here at this point saturation occurred, because continuously field current also increasing. At one field current, flux in the poles reaches constant. Maximum reaches after the saturation. Poles will saturate. No? Everywhere iron material will saturate after some magnitude of flux. Continuously flux cannot increase. That's why it is saturated. Now this point is saturation point. This is saturation. After saturation, flux is almost constant. Okay, whenever flux is constant, EMF also constant. It won't increase further. Let this is the rated voltage. Okay, now here we can draw, this is OCC. This is called open circuit characteristics, or what is the other name of this OCC? In labs, we write that. What is that? Magnetization characteristics. Magnetization characteristics. Why we call it is magnetization characteristics? Why we call magnetization characteristics? See, frankly to speak, in my engineering, I don't know anything. I don't know why we call it is magnetization. Just we are going the lab with fear of that persons. That's it. Not to learn subject. This is true. Magnetization is, I don't know at that time why we call magnetize, and why shunt field having more turns, series field having less turns, why it is thick wire, why it is thin wire. So these are all unknown things. Just going only for the sake of marks, but not at all useful, that is. So yeah, there is no use of that percentages. What is the use of percentage? If you have 80%, 90%, what is the use? Ultimately, we have to crack this competitive examination. For competitive examinations, marks are not at all important. Your subject only important. Okay. So at least whatever this 2-3 months time is there, you try to prepare like anything in your lifetime you never prepared. Just spend 2-3 months. Just spend 2-3 months like this. Enough. Okay. See here. This is called OCCR magnetization characteristics, because what happens here? Initially, how much flux is there? Residual flux. Initially, residual flux. After that, some flux added. Again added. Again flux added. Again flux added. Finally, up to what it reaches? Maximum flux. What is the nature of flux increase? We call magnetizing process it is. Flux decrease means demagnetize. Flux increase means magnetizing. That's why the corresponding characteristics also we call magnetization characteristics. We never call demagnetization characteristics, because flux increasing step by step. That's why we call it is magnetization characteristics. Okay. Now, initially, how much EMF induced? EG1 induced. Okay, EG1 initially. At that time, can we write the equation EG1 equals to ISH1 into RSH? Can we write like this? Can we write like this or not? Yes, we can write, because whatever EMF is induced, it is causing some current ISH1, and there is some resistance of field winding RSH. Now, voltage induced equal to ISH into RSH. That is only no, because EMF induced totally drop. It is equal to voltage drop in this. So this equation is valid. We can write like this. From this equation, tell what is the RSH field resistance. This is EG1 divided by ISH1. Okay. EG1 you can measure by voltmeter. ISH1 you can measure by ammeter if you place the ammeter here. If you place a ammeter and place a voltmeter across the armature, you will get voltage. EG1 is how much? Okay. If you know that voltage and current magnitude, you can find the RSH value. That RSH or this equation is similar to Y equals to mx or not? Tell me. This equation is similar to Y equal to mx or not? Here Y is what in the figure? This is Y. This is x. M means slope of the line. What is Y equal to mx? Straight line passing through origin. Okay. So in the same way, EG equals to ISH into RSH. RSH is nothing but slope here, M. So that RSH equals to EG by ISH. Now I will draw that line here. Observe it is RSH. Suppose this is EG1 and this is ISH1. The intersection of these 2 points. Now let us join the 2 points, because to draw the straight line, 2 points enough. Origin 1 point, another point. Another point I am taking this. Now I will draw this line extending. Wherever this line intersect the OCC, that is our operating voltage almost. That is the operating voltage. Wherever this line intersected the OCC, that is our operating voltages. wherever RSH, this is what field resistance line or slope of the line, slope. Okay, slope of the line passing through origin. Now, wherever this line intersect, the OCC, that is our operating voltage. If you observe, during the build-up process, voltage increase. After that, constant. Voltage is constant. Observe during that, the total voltage during the voltage build-up process. During voltage build-up process, the total EMF induced. The EMF induced in generator EG is equals to ISH into RSH plus additionally some more EMF induced. Why that? Why it is? Why it is? Additionally, see, actually this is EG1. Okay, this point is EG1. After that EMF induced, this must be EG2, but not it is EG2. EG2 is here somewhere. EG2, EG3, and so on. If you consider from here to here, this is what? RSH. What is RSH according to the equation? EG by ISH. But total EMF induced is here not only ISH into RSH, but also there is some rate of change of flux d phi by dt. Change in flux is there with respect to time or not? Yes. What is the flux initially? Residual, small flux. Now flux increase. Again flux increase. Now with respect to time, flux is changing or not? Yes. Whenever there is a rate of change of flux, an EMF will induce or not? Yes. According to Faraday's law, EMF induced. So the total EMF induced in the generator is equals to ISH RSH, resistance drop, plus a small EMF. So this is, we can write EG equals to ISH into RSH plus inductance of the field winding L into DI by dt. DI by dt. Which I it is? Field current. ISH is changing na here. ISH is changing. D phi by dt I am writing as L di by dt because phi equals to L into I. Okay, L into di by dt because current is changing. ISH1, ISH2, ISH3, and so on. And inductance of the field winding. Now, once saturation reaches, after saturation, let us assume saturation point it is exactly. Okay, so here it is saturated, almost after saturation, constant only, nearly same point it is. After saturation, what is the flux? Constant. Then flux constant means what is d phi by dt term? Flux constant after saturation, flux constant. D phi by dt 0. Constant, flux constant. What is the differentiation of constant value? 0. So this will be 0. So during voltage build-up process in a generator, there is an additional EMF induced in the field winding due to the rate of change of flux, and that EMF will disappear once the poles are saturated. See, at this point, what is the total voltage? This total voltage EG equals to ISH into RSH only. No EMF here. That is 0. Only this. At this point, total voltage is ISH into RSH. Okay. So all of you understanding this one or not? So during voltage build-up process, an additional EMF is there in the field winding due to rate of change of flux. Additional EMF. This EMF will disappear or become 0 after saturation of poles. Up to saturation only it is there. Okay, remember this. This is during voltage buildup. This equation is valid during voltage buildup. Suppose now voltage reaches constant. After saturation of poles, after saturation of poles, there is no rate of change of flux. There is no rate of change of flux. Means flux is constant, so no rate of change of flux. Hence, Eg equals to only ISH RSH. That's it. This is only the Eg after saturation of field poles. But during the voltage buildup means or before saturation, this is the total EMF induced. So you may get questions in self-excited generators before saturation of field poles. The EMF induced is dash. It is the sum of voltage drop in field winding plus an additional voltage EMF due to rate of change of flux. Both will be there. But after saturation, only voltage drop due to field resistance. EMF is induced, that is equal to field resistance drop. Okay. Okay. So remember this enough. So first of all, the condition is what? Residual flux. First condition is this. Now remember, residual flux upward direction, the flux produced by the field current also in the same direction. Then only voltage buildup will take place. This is one condition. Now write second condition. So all of you take this figure, completed figures, this OCC diagram. See, below the resistance line, whatever, suppose at this field current, how much voltage drop due to resistance is this much. This is ISH into RSH. And what is this remaining voltage here? This voltage is L di by dt. L di by dt. So that is L di by dt, L di by dt, L di by dt. And finally, L di by dt becomes 0 because saturation, there is no change in the flux. Second condition. Yes, the residual flux is due to property of material. RA is there, armature resistance drop is there, but very less, no, negligible that is, because field resistance is very, very high. Compared to field resistance, that armature resistance drop is negligible. That's why we neglect, and still it is under open circuit, no load condition, small current, that is, armature current is very small. Field, that is equal to field current. Small current, armature resistance drop generally neglected. That's why we are not taking. Okay, now write second condition. Second condition, the field winding terminals, the field winding terminals, the field winding terminals should be properly connected with armature. Should be properly connected with armature. Properly connected with armature. What is the meaning of properly connected? Yes, RSH will cut at the saturation only. After saturation at one point. Okay. Yes. Now, what is the meaning of that properly connection? Is observe here. So here we properly connected. That's why voltage builds up. Properly means whatever EMF induced initially Eg1 due to residual flux, that is causing a current ISH1. How that ISH1 is flowing in the field winding such that it is producing a flux phi1 in the same direction of residual flux. Then only voltage build up. Suppose by mistake wrongly connected. Wrongly means, let us consider here itself. By mistake, while connecting the field winding, you wrongly connected in this way. Wrongly connected. Reverse connected. Now check what happened. Due to residual flux, when we rotate, EMF induced, EG1. But due to that EG1, a current is flowing in the reverse direction or not? Yes. Compared to previous, now it is reverse. Okay, just listen, I'm not drawing all because I need to go to again original figure. Whenever field terminals are wrongly connected, due to the induced EMF EG1, a field current is flowing in the reverse direction to the previous. Now I'll come back to first figure. This is the current previously. Now applying right hand thumb rule, flux phi1 is coming upward direction, same as residual flux. Suppose according to wrong connection here, if field current reverse, let us reverse the field current. Let us reverse field current. Now flux phi1 will come downward direction. So whenever flux phi1 is opposite to residual, then what is the resultant flux here? Increasing or decreasing? Decreasing. So whenever resultant flux decrease, what is EMF induced? Also decrease. It won't build up. It is decreasing. That's why we should connect properly such that the produced field current should produce a flux in the same direction of residual flux. That is called properly connection. Okay. So if you want, you can take one point here. That is, the field current should produce a flux. ISH, field current should produce a flux in the same direction of residual flux. In the same direction of residual flux. Same direction means resultant flux increases. Step by step voltage also increases. Okay. Next, third condition. Next one, third condition. See, what is the third condition here is, see, this is regarding resistance of the field wind. Third condition is regarding resistance of field winding. There is some field winding here. Resistance of field winding is what? RSH. So can we take any value of resistance here? Can we design the field winding with any higher value of resistance? No. High value required, but not very high. There is one limit for this. That limit of resistance we call critical field resistance. So what is that name? Critical field resistance. That is, the resistance of field winding should be always less than critical field resistance. Then only voltage will build. Otherwise, no voltage builds up. So how to find critical field resistance? Yes, you can find critical field resistance. You can find from graph. How can we find? First write the point, then we go to that. Third condition. Third one, the resistance of field winding. The resistance of field winding should be less than critical field resistance. Should be less than critical field resistance. Critical field resistance. Let it is RC. Critical field resistance is RC. Resistance of field winding is let RSH. It should be less than critical field resistance. Then only voltage builds up. Now, what is the value of RC? Critical field resistance means what? So, in the competitive examinations, many times this question. Critical field resistance is dash. It is the rated resistance, minimum resistance, or maximum resistance. Tell me, critical field resistance is minimum or maximum? Maximum it is. Because the resistance of field winding should be less than that. Less than that. Then only voltage build. Suppose if it is more than that, no voltage builds up. Critical field resistance is the maximum field resistance. Above that, no voltage build up. So I will show you in graph how to find that. First, write the side heading, critical field resistance. the statement of this critical field resistance. Sorry, critical field resistance RC. So this statement is important. It is the maximum field resistance. It is the maximum field resistance above which the generator fails. The generator fails to build up voltage. Okay, it is important. It is the maximum field resistance above which generator fails to build up voltage. Okay, now let's see how to find critical field resistance. See, this is the OCC we got previously. EMF versus field current ISH. This is the OCC. It is the OCC we got at a speed n previously, and this is the field resistance line there, RSH. Let it is RSH1. This is our field resistance line we consider. Now how to find critical resistance here? Now field resistance is nothing but it is a slope of the line. Slope of the line only, no? According to y equal to mx and Eg equal to RSH into ISH. So here ISH means x-axis, Eg means y-axis, and RSH is nothing but slope of the line only. So if slope increase, nothing but slope increase, slope of the line increase, nothing but field resistance increasing or not? Yes, slope increasing means resistance increasing. Okay, now observe here. I am increasing the slope of the resistance line. Slope of the line I am increasing. Slope increases. Now it is RSH2. RSH2 greater than RSH1 or not? Yes, slope increase means resistance increase. Still increase the slope. Still I am increasing slope. At one instant, the slope of the line is almost tangent to the OCC. RSH3 tangent to OCC. Still increase the slope. Still increase the slope. This is RSH4. Now tell, out of these 4 resistor values, which one is the critical field resistance? RSH1, RSH2, RSH3, RSH4. Which is the critical field resistance? Yes, RSH3 is the critical field resistance. That is the maximum resistance. Up to that you can increase the resistor. After that, if you increase, generator fails. Why? Let us consider what is the order of resistor here. RSH4 greater than RSH3 greater than RSH2 greater than RSH1. Out of the 4, RSH3 is the critical resistance. Observe the figure. Corresponding to RSH4, see, corresponding to RSH1, this is the voltage builds up. This much voltage. RSH2, almost same voltage. RSH3, this is the maximum touching point. This much voltage still you will get. Voltage builds up to this. RSH4, what is the intersection point here? This much voltage only builds up. Almost residual voltage. Very, very, very small. That is negligible voltage. So voltage will not build after RSH3. So the resistance, what is the critical field resistance here? RSH3. That is the maximum resistance. Above that, generator cannot build voltage. So RSH3. So if you want to find that RC value, whatever the maximum touching point is there, measure that voltage here. Measure this voltage, how much it is. And correspondingly measure the field current and take the ratio of the two, you will get critical resistance value. Okay, like that we find in the actual graph also. But nowhere in objective type of examinations you will get questions like graph, questions on graph. only in the mains examination, they will ask this type of questions. Find the critical resistance value. They will give one tabular column, that is a practical readings, and based on that we have to draw OCC, and based on that we have to find this RC value, critical field resistance. Draw the tangent to the OCC, and wherever maximum it will touching point, from there measure voltage corresponding to this and field current corresponding to this, and take the ratio of the both, that is critical field resistance value. Okay, so critical field resistance is the maximum resistance. Above that, generator will not build any voltage. Next, fourth condition. Take the figure, complete this first. So di by dt will be increasing up to a particular point. After that again it decreases, because observe this figure, this one. See, up to a particular value it is increasing. After that this value decreasing again. Okay, first increase slightly and then decreases. Di by dt decreases. Next, fourth condition. Fourth condition. Write the condition first, then we see what it is. Fourth one. The speed of generator. Speed. EMF depends on speed also, no? So if you rotate at any speed, EMF will come? No. There is some minimum speed. Minimum, there is some speed. That speed you have to rotate. Otherwise, if you rotate at very low speed, EMF cannot build up again. Suppose slowly you are rotating. EMF will build? No. Because already residual flux is very, very small. And you also rotating very low speed. Then what is the product of the speed and flux? Almost zero. So you don't get any proper voltage. So in order to induce voltage and build voltage properly, there some minimum speed is required. That minimum speed here we call critical speed. That minimum speed we call critical speed. Okay, right here. The speed of generator. The speed of generator should be greater than critical speed. The speed of generator should be greater than critical speed. Greater than critical speed. Critical speed, let n see. Critical speed. Speed of generator n should be greater than critical speed. What is the critical speed definition now? Critical speed definition. It is the minimum speed or maximum speed? Minimum we have to rotate. More than that, you rotate any speed, voltage will come, but should not rotate less than that. So critical speed is the minimum value. Critical resistance is what? Maximum resistance, that is. So don't confuse in these two. Critical resistance is the maximum resistance, but critical speed is the minimum speed of generator we need to rotate. Okay, right here statement. Critical speed, it is the minimum speed of generator. Minimum speed of generator below which it fails. Below that, if you rotate below that, it fails. Below which it fails to build up voltage. It fails to build up voltage. Below which it fails to build up voltage. Okay. Now let's see how to identify critical speed. How to identify critical speed. See here. First, I'm taking the actual OCC. OCC, EG versus ISH. Let this is the OCC we got. At a speed N1 it is. It is the OCC at a speed N1 and it is the resistance of the line, resistance line RSH. Okay, RSH it is. Okay, it is the OCC at a speed N1 and this is the resistance line, field resistance line. We are not changing resistance, field winding same, fixed. RSH is fixed. Now what I will do is EG proportional to speed and flux. Okay, speed and flux. Flux flux is not changing, flux is fixed, flux is constant, reaches the saturation, constant flux. Now what I will do is speed I will reduce, speed, turbine speed I will reduce. Whenever speed of generator reduce, the EMF also reduces or not? Yes. Whenever speed reduce, the EMF also reduce. This is the OCC we get now. For this much speed, whenever speed reduces, EG also reduce. Let it is the speed N2. N2 less than N1. Okay. Now further reduce the speed of generator. Further reduce the speed of generator. So whenever speed is reduced further, at one instant, the speed, let it is N3 less than N2 less than N1. This is the order of speed. At one instant, that OCC will become tangent to the field resistance line. Now further reduce the speed of generator. Further reduce the speed of generator. Then your OCC will come like this. This is N4. Okay. So like that, whenever speed is reducing, EMF also reducing. At one of the speed, that OCC will become tangent to the field resistance line. Tangent. Now wherever it become tangent, that speed we call critical speed of generator. So this is the critical speed. So what should be the speed of generator to build voltage? Observe here. If it is N2, this much voltage builds up. If it is N1, this much voltage builds up. But if it is N4, how much voltage builds up? Only this much voltage. A small residual voltage, which is negligible voltage. This is negligible. So if you want to build voltage, you have to rotate the generators above the critical speed. Then only proper voltage will build. Otherwise, up to here only you will get voltage. Actually, all this will not come. Just it is showing. It won't come. It won't come. Okay, it won't come. This is wrong. This is only will come and stops. Further, no voltage buildup. Just for proper sequence drawing, this is also continuously up to this to show. Okay. Clear now? Critical speed is what? It is the minimum speed we have to rotate. Now, make a note here. How can we increase critical resistance of the generator? Can we increase critical resistance of generator? So previous point, that is previous condition. If you observe, this is the critical resistance. RSH3 is the critical resistance. Can we increase this value? Yes, we can increase. How to increase? If you increase the speed of generator, critical resistance also you can increase. This is one question many times in many competitive examinations and engineering services prelims also one question it is. See here, make a note of this point. Note. Observe first figure. Let us assume this is the critical resistance at a speed N1, e.g. ISH. This is the speed of generator N1. Critical resistance means we have to take tangent to this. Critical resistance means tangent to the OCC. Okay. This is RC1, critical speed, critical resistance. Critical resistance at a speed N1. Now I need to increase critical resistance value. Need to increase critical resistance means slope should increase. So when we can increase the speed of generator, your voltage will rise up. Then if you consider this is the OCC for a speed N2. Why? Speed N2 greater than N1. N2 increase, speed I increases. Speed increases. Whenever speed increase, now what is the critical resistance here? See, this is the critical resistance for second one. RC2 it is. Critical resistance of second. Resistance increases or not? Yes. So if you want to increase the critical field resistance, you should increase the speed of generator. So what is the relation between critical resistance and speed? Directly. RC proportional to speed. Therefore, the critical resistance is proportional to speed of generator. If you want to increase critical resistance, increase the speed of generator. When speed increases, RC2 also increase, or critical resistance also increase. So write that point. To increase the critical field resistance, to increase the critical field resistance, increase the speed of generator. Increase the speed of generator. Okay. See, these are the 4 conditions suitable for all generators. These are the 4 conditions suitable for all this all self-excited generators, shunt generators, series generator, compound generators. But if it is a series generator, one more condition required. Otherwise, voltage will not build. What is that condition? If it is a series generator, to build voltage, one more condition required. What is that? Tell me. What is the one more condition for series generator? If you catch up. Not laminations. Yes, load. Load is must. See, this is under no load condition. We are discussing all. This is no load condition. Under no load also voltage build up in shunt generator. But if it is series generator, observe here. Let us consider series generator. Series generator. Field winding in series with armature. Now tell me, it is open circuited. Load is not connected. Open circuit. Voltage will build in this. Under open circuit, question to all of you, under open circuit, the EMF induced in series generator is dash. The EMF induced in series generator is dash. Options: 0 volt, 7 volts, 220 volts, none of this. What is the answer? Under open circuit, EMF induced in series generator is dash. What is your answer? Okay. Some of you 0, some of you 7. Okay, good, very enough. The answer for this question is 7 volts. Why? Because there is a residual flux or not? Yes. Even there is no field current, residual flux is there. Condition is there, satisfied. So due to that residual flux, if you place a voltmeter also, it will show some EMF EG1, because whenever you rotate, a small amount of EMF will induce. That EMF is independent of field current. That is small voltage, maybe 5 volts, 6 volts, 7 volts, 10 volts, anything is the answer. Okay. But after that, there is no current here because it is open. Due to that EMF, how current will circulate here? No current will circulate because open circuited, no. But in shunt generator, what happened previously? Even there is open circuit, there is a path for field current here. That's why current is circulating, step by step voltage builds up. But in series generator, there is open circuit, no current will flow, because if current is not flowing in field winding, no flux will produce. That's why that 7 volts only continuously will be there. After that, no voltage buildup. If you place a voltmeter across this, it will show 7 volts. See, example I given, and some of you may ask again, sir, in examination 7 is not there, none of this is there, I put none of this. So don't do like this. 7 is just example I given, maybe 6 volts or 5 volts or 2 volts or 10 volts. These are all answers. Small voltage, whatever is there, that is the answer. Clear? Now same another question. Under open circuit or under no load, both are same. Under no load, the EMF induced in shunt generator is dash. The EMF induced in shunt generator is dash. Well, what is the answer? Same option, 0 volt, 7 volt, 220 volt, none of this. What is the answer for this? What is the answer? Yes, very good. The answer is 220 volts. Don't say 0 here. 0 you never get in self-excited generators under open circuit or no load condition. If it is series generator, there is a small voltage. If it is shunt generator or any compound generator, there is rated voltage. Rated, maybe 220, 230, 240, 200, anything. That rated voltage will be there. Why? Just now I said here. See, under open circuit, you place 1 voltmeter here. Place 1 voltmeter. And if you rotate, how much this voltmeter will show under open circuit? Rated voltage immediately. So how much time the generators will take to get rated voltage? It will take 1 minute. Slowly, step by step will come. No, just in 2-3 seconds. Just in 1 or 2 seconds also, if you see the voltmeter reading, you will get rated voltage in that. Immediately, once you start rotating, quickly voltage builds and reaches rated constant voltage, 220 or 230. This voltmeter continuously shows 220 or 230, whatever rated voltage. It will build up to rated, but series generator, it cannot build because no path for current in this. That's why, what is the additional condition for series generator? It must be connected to a load in order to build voltage. Otherwise, no voltage build up in series generator. Okay, so write that point here. In order to build voltage in series generator, in order to build voltage in series generator, it must be connected to a load. It must be connected to a load which is variable. Variable load means current also varies, flux also varies, EMF also varies. That is, increase the load step by step, 2 amps, 5 amps, 7 amps, 10 amps, like that. Whenever load magnitude increasing, if you connect a load here, if it is variable, current increases. Whenever current increase, flux also proportional to current increases, EMF also increases, or voltage builds up. That's why I said variable it is. Okay. So remember these two questions important. Series generator, small voltage. Shunt generator, rated voltage. Okay. So still it is not completed conditions. Conditions over, but there is some important observation. So after break we see. So take a break. Take a break. See, particularly in self-excited generators, what are the main conditions? We have discussed four conditions. Residual flux should be there. The field winding should be properly connected. Field winding should be properly connected. Okay. And resistance of field winding should be less than critical field resistance. Speed of generator must be greater than critical speed. These four conditions. And if it is series generator, the condition is load must be connected to build the voltage. Otherwise, voltage will not build. Okay, these are the conditions made. Now, assume that all conditions satisfied. While designing a generator, all conditions are satisfied. Now, out of these conditions, which condition may fail after some years or months or days due to aging effect? That is, we call aging effect. Due to aging effect of generators. Aging effect means if age of generator increase, old one, definitely as years increases, strength of every material decrease. So in the same way, residual flux is not permanent flux. Residual flux is a temporary flux. It will present for some time, not permanently. Suppose if the generator you are not operated, mainly in the engineering labs, in engineering colleges, whatever the DC machines lab is there, main problem there it occurs. Why? Because these labs mostly regularly they don't operate. Suppose your semester is over. In the next semester, that lab will not be there. And again, your junior has to come in the next semester. Or let us assume it is there also. And particularly if you see in the lockdown period, there is no colleges at all for 6 months or 1 year also. Then if it is not operated for a long time, is there residual flux present? If a self-excited generator is not operated for long duration, then the residual flux will become zero. That is due to aging effect also. Age increases, or if it is not operated anything, due to aging effect, the residual flux will becomes zero. The residual flux will becomes zero. Then after some months, you started the generator. Do you get voltage? No voltage you get, because there is no residual flux in that. Remaining conditions all satisfied, but residual flux has become zero. If you rotate it infinite speed also, you don't get any voltage, because this is not there. It is very important for self-excited generators. Now it becomes zero. Now tell me how to reproduce this. How to reproduce? Whenever residual flux becomes zero, the generator fails to build a voltage. So it requires again residual flux to build the voltage. How can we reproduce? Therefore, the residual flux can be reproduced by two methods. The residual flux can be reproduced by, one method is operating generator as a motor for some time. Operating the generator as a motor for some time. How much time? At least 30 seconds also enough. Operate the generator as a motor for some time, enough. If you operate as motor, you give supply to that. You will give supply, no? So we are giving supply to motor. Then field current will flow, flux will produce, and motor rotates. Let us operate the motor for some time, 30 seconds like that. And then remove the supply to motor. Now stop the motor and then start your prime mover, mechanical input. Now voltage will build, because whenever you remove the supply to motor, the flux whatever is produced previously, it will not become zero immediately. For some time it will be there. Now like that we can produce residual flux. That is one method. And second method is by using field flashing we call. By using field flashing. What is field flashing? Simple. field flashing is, see, let us consider it is a shunt generator. Shunt generator it is. Now whenever we rotate, EMF is not inducing, EG is 0 because residual flux is not there. Now what we have to do is remove the field winding from armature. Remove the field winding from armature, excite with a field winding separate. Remove the field winding from armature, give supply to only field winding. Now there is a field current in the winding and some flux will produce. Okay, let us apply the voltage for some time again, maybe some 10 seconds, 20 seconds also enough. Now remove again back the field winding from the supply, connect the field winding back to armature. Now start the generator. Now there is EMF induced. Means residual flux is produced by giving supply to only field winding. This method we call field flashing. This is called as field flashing. Now which method is best? First one or second one? Operating generator as motor first. Second, using field flashing. Which method is the best method? One or two? First one or second one? Okay. So most of you given first. Some of you, some means very few, that is two. Okay. Okay. Let's see which one is right. The right answer is second one. Second one is the best method. Second one is best. So I think why you people choose first one is it is easier. You think that it is easy operating generator as motor just by giving supply to that, but that is difficult. At the same time, if you operate the generator as a motor, there is so much power loss. Suppose it is a shunt generator. Let us give supply to this as a motor. Now when you give supply, there is armature current, there is field current. Now motor is rotated. Motor is rotated. So when it is operating as motor, there is a field copper loss, there is a armature copper loss, and motor is rotating, there is a mechanical loss, bearing friction loss. So this much power loss is there when you operate as a motor, more power loss. But second one, field flashing. What you are doing in field flashing, we are giving supply to only field winding like this, only field winding. Then how much loss is there? There is a field current. That's why there is only field copper loss, I square R, and no armature copper loss, no mechanical loss. So power loss is less here. Power loss is less. So which is better? Saving power is better or wasting power is better? Saving power is very important for electrical engineers. So that's why we need to save power. And this is the most easiest method in the labs. Easy or not? Most easiest method. How? Try to remember your lab experiments. So there is one board panels. Panel boards will be there. Shunt generator, series generator, like that. Generators. So on that panels, they will indicate terminals. F, FF, field winding here. A, armature here. Like that indicated, no? Okay. Have you remembered this? Like that, terminals will be there on the board. If you want field flashing, just take a small battery and connect to the field terminals directly here with wires. Very, very easy it is. Compared to operating as motor, this is better. In the labs only it is useful. But if it is in your home, that is difficult. Suppose you are using DC generator in your home, for example. Whenever it is not generating voltage, then which one is best at that time? Operating it as a motor only best. Okay, but which is efficient? Second only efficient. No power, very small power loss in field flash. That's why field flashing is preferred always. What is field flashing? In field flashing, exciting or giving supply to only field winding by removing from armature and create residual flux, then reconnect back to armature and then start it as a generator. This is called field flashing. Okay, field flashing is consuming less power when compared to operating the generator as a motor. That's why we preferred always second, field flashing method. Okay. Clear now? Field flashing, Nehali? If residual flux is zero, then OCC will start for zero. Now, OCC will not come first. If residual flux is zero, how EMF will come? There is no voltage buildup first. Okay. If residual flux zero, voltage zero only. It won't start from zero. Totally zero only. Okay. Remember that. See this question. See this. What is answer? A DC shunt generator, when driven without connecting field winding, shows an open circuit terminal voltage of 12 volts. When field winding is connected and excited, the terminal voltage drops to zero because what is the answer? First understand question. In a DC shunt generator, when driven without connecting field winding, means field winding not connected, means field current zero. Whenever field current zero, then it shows a open circuit voltage of how much voltage? 12 volts. This is called residual voltage, residual flux. When field winding is connected, after connecting field winding, the terminal voltage drops to zero. When field winding connected, voltage drops to zero. What is the problem? Field winding has wrongly connected. That's why I said, in order to build voltage, you should connect properly the field winding. Okay, then only voltage builds. Properly means what? When field winding connected, field current will flow. That field current will produce again a flux. That flux should be added to residual flux. Then resultant flux increases, voltage also increases. But what is happening here? Voltage decreases to zero after connecting field winding, means the current is flowing in reverse direction, flux produced opposite to residual flux. That's why resultant flux is becoming zero, voltage also zero. The answer is the field winding has got wrongly connected. Okay, that is the problem. Maybe you people may guess that the field resistance is higher than RSH greater than critical resistance. Here also voltage will not build. Okay, what is the condition for resistance? The resistance of field winding should be less than critical resistance. Then only voltage builds up. If it is higher, voltage will not build up. But here, problem is not this. Wrong connection is the problem because voltage becoming zero. No, if it is a condition, here voltage builds up to some small residual voltage. It will be there continuous, but voltage zero because of wrongly connection. Okay, clear this one, all of you. Next question. Now answer this. A shunt generator has a critical field resistance of 200 ohms at a speed of N1 equals to 800 RPM. Okay, if the speed of generator increased to 1000 RPM, speed increases, then what is the change or what is the new value of critical field resistance? RC2 is how much? What is the new value of critical resistance? So already we know critical resistance proportional to speed of generator. If the speed increase, critical resistance also increase. So apply this. RC2 by RC1 equals to N2 by N1. Now what is the RC2? RC1 is 200 into N2 is 1000 by 800. What is the answer? Yes, 250, correct. 250 ohms. The new value of critical field resistance 250 increases to 250 ohms. So directly you can strike out these two. Definitely answer is increase. But how much? For that we need to find it. 250 ohms. Okay. Next question. So this question you need to answer. So much confusing questions only. This one of whatever we are going to see now. Try to answer carefully. Okay. Write the question. A DC shunt generator produces rated voltage. Produces rated voltage of 220 volts. 220 volts at a speed of capital N RPM. Capital N RPM. Okay, full stop. If the direction of rotation is changed, then the voltage induced is dash. The voltage induced is dash. Options: 220 volts, 0 volts, minus 220 volts. None of these. What is the answer? No, value of RC 250 only, because already it is 200. Previously how much? It is already 200 ohms. After increasing the speed, new value is this one 250 only. It is not 200 plus 250. Okay, new value increases to 250. All of you, what is the answer? Okay, whatever, just try to answer so that you will get interest. That's it. Okay, enough. So mixed answer, somebody 200, 220, 0, minus 220. Answer for this question is 0 volts. See, the answer for this question is 0. Voltage will not build up in this. 0 voltage will become 0, means no voltage further. 0 is the answer. So to understand this question, you have to remember the previous two figures. One is machine diagram I drawn previously at OCC characteristics, open circuit characteristics, and one more the shunt generator, this one. See, for all these questions, total 5 questions will come. For all these, the figures are same. Every time I don't draw, try to remember this diagram. So 2 pole, so first we will take one reference diagram. Here voltage builds up. Here voltage builds up. Initially given a rated voltage 220. So for that I am taking one direction, clockwise I will take. So this is the connection at that time. See, I am considering the rotation at that time is clockwise. At a speed n it is rotating, and residual flux I am taking upward direction. This is the residual flux. Okay, residual flux. Here voltage builds up to rated voltage of 220 volts. 220 volts builds up. When you place a voltmeter, it will show 220 here. Whenever it is rotating clockwise at a speed n, assuming that Eg proportional to n5, direction of rotation n positive, I am taking clockwise means positive, and residual flux is upward direction, that is positive. Okay, Eg proportional to direction of rotation positive, I am taking clockwise means positive, flux is upward direction, residual flux, that is positive. Positive, positive, overall positive it is. Positive polarity means this is plus, this is minus, according to this figure. Now current is flowing in this direction, ISH. Residual flux and whatever field current is flowing, that is added with residual flux. So field current is flowing such a direction, it produces a flux in the same direction of residual flux. So you try to print these two figures in your mind. This is our reference for all questions from now. Okay, so try to print every time you don't draw the figure, same figure for every question. Now try to print this in your mind. Residual flux upward direction, flux produced also in the same direction, then voltage further increases up to rated voltage of 220 volts. Now voltage builds up. What is the question now? Direction of rotation reverse. Residual flux is same, not mentioned. That's why, see, proceed like this. Direction of rotation, residual flux remains same. That's why I'm taking upward direction, same as upward. Okay, residual flux, I'm indicating like this. Okay, now what is Eg? Proportional to n into 5. What is the direction of rotation now? Reverse. So minus n I am taking. Residual flux remains same. Don't change. Same as it is. Here minus, here plus. What is the overall polarity? Negative. Minus plus means negative. Means EMF polarity changing or not? Yes. Whatever EMF induced, that is reverse. So previously it is positive here. Positive means here plus, here minus. Now negative EMF means EG reverse or not? Yes. Polarity of EMF is reversed. When EMF reverse, field current here will reverse or not? If it is plus, current is going like this. But when it is plus, here minus, reverse, then field current will flow in this direction. So whenever field current reverse in the winding, what is the flux phi1 direction? Also reverse. Whenever field current reverse, ISH reverse, that's why phi1 whatever is produced, that is also reverse. Reverse means previously upward direction, now you have to take downward direction. This is the flux. Now what is the two fields here? Opposition or not? Yes, the produced flux is coming opposite to residual flux. That's why resultant flux decrease. Finally voltage is 0. Once voltage is 0, no current, no flux further, totally EMF is 0 on. No voltage builds further. Voltage drops to 0. Clear all of you this? Okay. So load is not connected. Under no load, we are considering all of this. Next. After one more question, all your doubts will be cleared. Okay. See, for motor, no problem. For motor, no problem. Don't think of motor here, because motor you are giving supply. If you change the supply accordingly, direction of torque will from motor will rotate. These conditions are not for motors, only for generators. See, this figure you have to consider as a reference diagram. Rotation is clockwise. EMF is positive polarity, means here upward direction. Field current is upward direction. With this field current, flux phi1 is upward direction. Now both fields are same direction. Voltage builds here. Now according to question, we are changing. What is the question? Direction of rotation reverse. So I reverse minus n. Flux is remains same, not mentioned. And what is overall polarity of EMF induced? Negative, opposite. So whenever EMF is opposite or negative, field current also will flow in reverse direction. that will produce a flux in reverse direction. That is I taken here. So resultant flux decreases. So further voltage not build up, decreasing to 0 finally. Okay. Now write one more question. One more question. Now for this second question, 100% I will bet everyone will answer properly. Let's see. See that question. Let's see you can able to answer or not. Write the question. Same question, same above question, only little modifying again. Let write that in the above question. In the above question, in addition to direction of rotation, in addition to direction of rotation, residual flux also reverse. Residual flux also reverse. Then the voltage induced is dash. The voltage induced is dash. Same options I'm giving. 220 volts, 0 volts, minus 220 volts, none of this. What is the answer? Yes, I can expect. First try to answer. So these, whatever the 5 questions we are discussing, these 5 questions are ESC mains questions. ESC mains question given these 5, whatever we will see now for conventional examination. Same questions repeating in the competitive examinations also. Same type of questions. Okay. Okay, enough. Wait. See, your answers are most of you given minus 220 and also 220. And somebody option D also given. Okay. 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 Whatever you tried well, but answer for this question is 0. So what you are thinking now is in the previous question, residual flux phi1 coming opposite, but whenever residual flux is reverse, both will come in same direction, like you are thinking. Most of you I think, but you don't change directly here itself. Again start from starting. Again from the starting. What is starting? See here. What is they said? In addition to direction of rotation, residual flux also reverse. So reverse the residual flux first. I reversed. Okay. Residual flux is reversed. Now Eg proportional to n phi. Direction of rotation already reversed, minus n. In addition to that, residual flux also reversed. So take minus it is. Now what is minus minus? Plus means EMF polarity, whatever is there previously in the original condition, same is there now also. If EMF polarity is same, field current also same direction or not? Yes, same direction field current is flowing. If field current is same, flux phi1 also same direction or not? Yes, phi1 also same. Same means which one? That same. This diagram you should not forget. Phi1 same means this is upward. Like this only phi1 is there, upward direction. Phi1 is in this direction. Now what is the resultant flux here? Increasing or decreasing? Decreasing. So finally EMF also 0. No voltage build up here. Clear? See, this is only reference for all questions. Here voltage builds up. Clockwise direction, residual flux we take in reference upward. Phi1 produced also in same upward direction. EMF builds, positive it is. Now according to question, direction of rotation reverse. In addition to that, residual flux also reverse. So I reversed here already, residual flux. But EMF polarity I am getting same. field current same, flux phi1 also same as previous. That's why same upward I taken. So resultant flux is opposite direction. That's why decreases to 0. So all of you clear? Just raise the hand. Still, some of you may have still doubts, but try to analyze. After one more question, your doubts will be cleared again. Okay. Next. Next, one more question. Same, in the same question, one more I am changing. Try to answer this. Completed this? Write the question. A shunt generator produces rated voltage of 220 volts. 220 volts at some speed n, same as it is. Full stop. If the field terminals are interchanged, if the field terminals are interchanged, then the voltage induced is dash. Then the voltage induced is dash. Voltage induced is dash. Same options. 220 volts, 0 volts, minus 220 volts. None of this. What is the answer? Answer is dash. Now again analyze, same as the previous question. Yes, very good. Yes, very good. All of you given right now, answer is 0. 0 only, because that is one condition. In the conditions we have seen, third condition, second condition, that is connect the field winding properly with armature. Means whatever field current is producing a flux, that must be in same direction of residual flux. But what is changed here? Field terminals are changed. Then field current definitely reverse. When field current reverse, flux also reverse. Means this is residual flux, same. EMF is what? Direction of rotation, residual. So these two are not mentioned. Means this is remains same, positive only, no change. Field current, actually field current should flow same direction, but ISH will reverse. Why ISH reverse? Because field terminals are reversed here. Field terminals are reversed. That's why current is reversed. ISH reverse. Then what is the flux phi1? Also reverse. Phi1 is opposite. Now resultant flux is what? Decreased. So EMF also decreased to 0. That's it. Got it now, all of you? Yes, all of you right. Field winding terminal reverse means field current directly reverse. Next, one more question. Next question. See this. A DC shunt generator. So all of you completed previous. Very good. One more question. A DC shunt generator produce rated voltage of 220 volts. 220 volts. Stop. If residual flux only reverse, if residual flux only reverse, then voltage induced is dash, then the voltage induced is dash. Same options: 220 volts, 0 volts, minus 220 volts, none of this. What is the answer? Initially rated voltage. Now residual flux only reverse. Here you should not get doubts, sir. How residual flux reverse, why it is reverse, how can we reverse? This type of doubts you should not get. Whatever is given, you proceed, you will get the answer. But if you think more than that, you never get the answers. Okay, whatever they given, you apply that. That is only engineering. Don't think beyond that. What is answer for this? Yes, very good. See, don't say less than 220. From the options, what is the correct one? Yes, most of it given right now. That is option C is correct. That is minus 220. Minus 220 is the correct answer. Minus 220 is correct. Okay, see why it is minus 220. What is initially flux? Initially I'm taking when rated voltage is there at that time, residual flux upward direction, phi 1 also upward direction. Now voltage builds up here. How much voltage builds? 220 volts will come. This is the first case. Now what is the change given? Eg positive here. Eg proportional to direction of rotation and residual flux. That is I am taking as positive reference. At that time this is the flux. Now I will apply the change. What is the change? Residual flux only reverse. So I will reverse residual flux. This is easy to analyze. Every time we cannot draw the figure. No? This is easy and simple. And residual flux is I reversed. Now I need to check EMF. What is EMF? Eg proportional to direction of rotation not given. So write same N. And residual flux reverse. No, that's why minus residual flux. Now what is the polarity of EMF? Positive negative will become negative. Means EMF inducing in reverse direction. Minus negative opposite to previous. Now let us check. As EMF negative, what is the field current direction? Also reverse. Field current will reverse. When field current reverse, what is the flux produced? Also reverse. Reverse means opposite to this original. So let us take opposite. This is the phi 1. Now both same direction or not? Yes. Still voltage as resultant flux increase, still EMF increase. But what is the finally that EMF increasing in the reverse direction only? Negative, 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 up to minus 220 again will come. Yeah, whatever is the rated voltage 220, again you will get in the reverse direction minus 220. Okay, got it all of you know? All of you clear now why it is 220 minus 220? Once more. Okay, initially this is the reference we taken. Residual flux in upward direction, phi 1 flux produced also same direction. Voltage we are getting 220 positive, EMF positive. Now according to question, we reverse residual flux. So reverse opposite to this I taken. Okay. After that I verified EMF is what happened. Rotation is not mentioned. Only residual flux reverse. So I reverse minus. So overall I'm getting negative EMF polarity. Whenever EMF is reversed, corresponding field current also reverse in the winding. flux also reverse, because flux depends on right hand thumb rule. Whenever current reverse, flux also reverse. Which phi 1 reverse? Reverse means actual phi 1 is upward. Now I reverse that phi 1. Now I observed both are getting in same direction but opposite to previous. That's why flux still increase and EMF also increase, but negative voltage you get final. Opposite polarity. Clear now? All of you. Once more clear. Okay, one more question. See, one more question, last question in this. In this last question. Try to answer. A shunt generator produce rated voltage. Rated voltage of 220 volts. Stop. If in addition to direction of rotation, in addition to direction of rotation, field terminals are interchanged. Field terminals are interchanged. Field terminals are changed. Interchanged. Then the voltage induced is dash. The voltage induced is dash. Same options. 220 volts, 0 volts, minus 220 volts, none of this. What is the answer? Answer. Okay, again, some of you 0, 220, minus 220. Okay, take time, try to analyze slowly. For this type of questions, you never by heart the question and options. So learn and forget. So whenever is required, at that time you try to derive, because don't stress your mind, because remembering every question and options is difficult. Try to learn subject and forget. That is best. Now also most of you saying 0. Okay, mixed answers still. Zero because field terminals interchanged. Okay. Okay, see this. See here. Again, first reference is what? This is residual flux upward direction. Phi 1 also upward direction. Then EMF is positive, direction of rotation clockwise. Residual flux upward direction. Positive. It is, we assume positive, and EMF 220 here. This is our reference. Now what is given? In addition to direction of rotation, means direction of rotation reversed. At the same time, field terminals are interchanged. At the same time, field terminals are interchanged. Whenever direction of rotation is reversed, Eg proportional to residual flux not mentioned. That's why I'm taking same direction. Same as previous, upward. Now Eg I will check. Direction of rotation is reversed, minus n. And residual flux remains same. So take it is same. Now what is the overall polarity? Negative. But previously EMF positive. When EMF is negative, actually field current has to be reverse, but it won't reverse, it will be same direction. That's why phi 1 is same direction. That's why phi 1 will come in the same direction of residual. Same, both are same. Previously upward, now also same direction. So Eg is inducing, EMF is inducing, but negative, na it is. EMF is inducing here, but negative. Try to observe that. Flux increase, magnitude of flux increase, but overall EMF negative. That's why finally the answer is minus 220 volts. Still doubt? Still required clarity for this? Yes, I will tell why ISH remains same. Okay. See, forget means if you learn subject, you never forget. If you try to learn subject, you never forget. But if you just listen, and then definitely you will forget. So here, observe the question. What is said in addition to direction of rotation? Actually, this is the first diagram. This is the first diagram. I am drawing again first diagram it is. Direction of rotation clockwise. This is EMF induced is Eg proportional to N phi. Same clockwise is positive, residual flux upward direction. Now EMF is positive, that's why it is a polarity Eg plus minus. Due to that EMF induced, a current will flow in this direction ISH1. This ISH1 will produce a flux phi 1 which is in the same direction of residual flux. Okay, this is original reference figure it is. Now what is said, in addition to direction of rotation, field terminals also interchange. Means direction of rotation is reverse. Observe the figure. Direction of rotation is reverse. At the same time, field terminals are interchanged like this. When direction of rotation is reversed, let us take anti-clockwise direction. What is EMF polarity now? EMF polarity depends on speed and residual flux. So minus N, direction of rotation reverse. Residual flux, no, it is not mentioned, same. So what is EMF polarity? Negative. So it is positive. Take negative means opposite. This is EMF plus minus. But at the same time as the field terminals are interchanged, plus means current will flow in this direction, in this direction, in this direction, like this. This is ISH1. This ISH1, this ISH1, same direction or not? Yes, same direction means residual flux is same, upward. Now field current ISH1 same as previous, so phi 1 also in same direction. So resultant flux is increasing or not? Yes, increasing. But what is overall EMF? Negative. That's why minus 220 will come again. Clear now? Why flux phi 1 remains same? Because of this reason. All of you raise the hand. Okay, good. So all of you clear? Why ISH remains same and phi 1 remains same? Why not 220 means EMF is negative, no polarity. Previous EMF positive plus 220. Now EMF negative, no? That's why minus 220. Okay. Yes, in addition to direction means already direction reverse. In addition to direction of rotation, field terminals also reverse. Otherwise, you write clearly in your question. In addition to direction of rotation, field terminals also interchange. Okay. Yes. Even though connection is reverse, field current remains same. That's it. Okay. So is it enough? So again, go through all the question once slowly, then you will understand again. Yes. Okay. So with this, our shunt generator, we complete one of the self-excited DC machine. Now series machine. In the self-excited DC machines, second one is what? DC series machine. Second one is DC series machine. DC series machine. So both generator and motor simultaneously we see first generator. Check the figures. Series generator or series machine is field winding connected in series with armature to produce the required flux. That's it. This is the field winding connected in series with armature here, like this. In series with armature. Same conditions here also. Whenever we rotate an EMF induced in series generator, EG. And here armature current, field current, load current, all are same. Okay. Terminal voltage. This is direct machine representation. If it is an equivalent circuit of this field winding in series with armature. How to represent series field? Less number of turns and thick wire. The representation of series field winding is less number of turns and thick wire. Why it is thick wire? Because as the field winding connected in series with the armature and load, in series with armature and also in series with load it is. That's why the resistance should be less. Otherwise, if resistance is high like shunt, most of the voltage will drop here itself. Whenever current is flowing, most of the voltage will drop in the field winding itself. That's why we keep the resistance very low, less than 1 ohm almost, just like armature resistance. Just like armature resistance. Okay. So as it is required low resistance, this series field winding should be made up of thick wire. Low resistance means more cross section. That's why it is a thick wire. And it should have less number of turns or more number of turns. Less number of turns. Opposite to shunt. Less number of turns we use. Why less turns? Flux proportional to MMF. N into I. What is the current passing through this winding? High current or not? Load current or armature current? High currents they are. Already current is very high. Then you no need more turns. You can reduce the number of turns. So for the same flux like shunt, if you want, you can reduce number of turns. Not required. Any one is enough. Current is already high. That's why reduce the number of turns. That's why the series field is always represented with thick wire and less number of turns. Okay. So if you write KVL equation of generator, so write one statement first here. In series machine, the field is excited from armature. The field is excited from armature by connecting in series. By connecting in series. So as it is series, the field winding should have low resistance. It should have low resistance. It should be designed with low resistance. Comma, it is made up of thick wire and less number of turns. less number of turns to produce the required flux. To produce the required flux. Okay, to produce the required flux. Now write the KVL equation on this. KVL. What is the KVL equation? EMF induced is EG, that is equals to output voltage V plus drops in this. Same current is passing in armature resistance and also field resistance. That's why IA into sum of these two, RA plus RSC plus brush drop. So this is KVL equation of series generator. Now if it is motor, you write the equation for this motor. If it is motor, draw the second figure only and reverse the direction of current. Next, motor. Series motor. Only second figure I am drawing. Field winding in series with armature. Current is reverse. Motor will take the current IA equals to ISC equals to IL RSC RA. The EMF induced in motor we call back EMF. Now write the KVL equation of motor is input voltage is V equals to EMF induced in armature EB plus drops. Same drops RA plus RSC plus brush drop. This is the KVL equation. Next, third category in self-excited is compound machine. Compound machine. Third one, DC compound machine. DC compound machine. Compound means mixing. That is both shunt winding, series winding, both we utilize. Shunt and series. In this machine, we will have two windings, field windings, shunt plus series. Both field windings we utilize in these machines. Both field windings we utilize, shunt and series both. So where field winding located? Pole core. Field windings we place on the pole core only. Both will be there now, shunt and series. Both excited from armature only. Self-excited means the field current will come from armature only. Okay. Now in DC compound machine, totally we have three categories. Three categories, like one by one. First, write one statement here. In this machine, both shunt and series field windings. In this machine, both shunt and series field windings are placed. Both shunt and series field winding are placed on the pole core and excited from armature. 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 Right. First category in this side heading. See, when there is two field winding, there is current in two field windings. How that current is flowing? Same direction or opposite direction? Okay, based on the direction of current, there are two types. One is cumulative, second is differential compound. Okay, write that side heading. First one, based on direction of current, based on direction of current in the field windings. So when there are two field windings, both will carry current. If it is same direction, one type. If it is opposite direction, another type. Based on direction of current in field windings. Based on these two types we have. There are two types. One is cumulative compound DC machine. Cumulative compound DC machine. And second, differential compound DC machine. Differential compound DC machine. Cumulative compound DC machine, differential compound DC machine. Write the first one, cumulative compound DC machine. First, cumulative compound DC machine. First one. Cumulative compound DC machine. Cumulative compound means additive. The flux should be additive here. For that, the two field windings should carry current same direction. Like that, we have to arrange the windings. That itself will not carry current same. We have to arrange during manufacturing stage itself. We have to arrange the winding. Consider this is the pole core. One field pole I am taking. One field pole I taken. So there are two field windings on that, on the pole core. This is the first shunt field winding. This is shunt field winding. Any winding you can place, shunt or series, anything you can place. But for mechanical stability purpose, we place shunt first because more number of turns it is. That's why we always prefer shunt field winding. If it is pole core, place the shunt field winding on that, more number of turns. Okay, this is shunt. And on that, let us place series field winding, less number of turns. This is series field winding. Okay, both are placed on it. Now internally both windings are connected with armature. So that connections also we will see, long shunt, short shunt, how it is connected. Now let us consider here, shunt field is carrying current cross here, dot here, cross dot. Apply your right hand thumb rule. 4 fingers goes inside in left side and comes outside in right side, and flux is coming downward direction. By applying right hand thumb rule, the shunt flux is in downward direction. If you want cumulative compound, arrange the series also such that it should also carry current same cross dot. Now series flux also will come in the downward direction. Now under one pole, what is the resultant flux? Under the pole, the resultant flux is sum or addition of the two fields. That is called cumulative compound. The fields are additive. In order to get addition, the two field windings should carry current same direction. If it is same, we call cumulative compound. Okay, write the statement. For cumulative compound, the two field windings should carry current. The two field windings should carry current in the same direction. Should carry current in the same direction. Then resultant flux under the pole is additive. Resultant flux under the pole is additive. Under the pole is additive. The resultant flux under the pole is additive. Now, what is differential? Simple. Let us reverse any one current. Suppose series field winding current reverse. Then series flux will come upward direction. So both flux is opposite direction. Resultant flux is subtractive nature. That is differential compound. Okay, right. Differential compound. Differential compound DC machine. Again, on the same pole core, the two field windings, shunt field and series field. So these two windings are arranged such that the current is cross in shunt dot here, and now here dot, here cross. Shunt flux is downward only. Apply right hand thumb rule. Shunt field is downward, but series field will come in upward direction under one pole. Now the resultant flux under the pole is subtraction, minus. Means resultant flux decreases. That effect we call differential effect. Okay, right here. For differential compound, the two field windings should carry current. The two field windings should carry current in opposite direction. In opposite direction. Hence, resultant flux under the pole is subtractive. Okay. So everyone is under hungry mode. So remaining two categories are there. So we continue. This is tomorrow. Remaining two categories. So second category based on compounding. We have over compound, flat compound, under compound. And third category is type of connection. How you connected inside, long shunt connected or short shunt connected. So based on the two types, the long shunt and short shunt. Okay. But mainly two types only they are. Cumulative, differential. In cumulative again we have three types like over compound, flat compound, under compound. Okay, in cumulative only we get three types. Differential only one. Cumulative again three types. That is based on compounding. We will divide them. Okay. So tomorrow we continue the same. After completion of this compound, types is completed. Then the actual topic is after that only will start, like armature, reaction, commutation, after types of DC machines. Okay. So tomorrow armature reaction will be there, very important for every topic from there. So don't absent by tomorrow.
Sir.
Oh, tell me.
Sir, my doubt is first regarding residual flux, sir.
Tell me.
Sir, in all the previous faculties, when they taught in OCC characteristics or synchronous motor also, they did mention about this even starting from y-axis.
Even?
Even starting from y-axis. So
because
this residual flux is essential for all the kinds of motors or generators. I mean,
not all generators. Separately excited generator, no need of residual flux. For separately excited, is it required residual flux? You are giving separate excitation. No? Then,
sir, but yes, sir. But in that case, he did draw it from y-axis only, sir. He started it rather than here. He started it a bit up.
Actually, not required. So that must be, that can start from zero only, because field current zero, flux zero. Because you can design that material so with no property of residual flux, not required. No. then
Yes,
at
sir.
that time it starts from zero on. When
Okay,
field
sir.
current increase, flux increase, EMF increase. But
And
self-excited generators must start from here.
yes, sir. And sir, another thing, sir.
Hmm.
In this case of self-excited only, like
Hmm.
for instance, this DC motor, like what you said, after 6 months of nobody is going to labs, I'm going to start this generator.
Hmm.
Unlike other generators, like why can't first initially current is going, then slowly flux is building up? Isn't that flux like why can't it operate like other motors? Why it should have this residual flux only particularly in the case of self-excited DC? Like it would
Self
normally start.
self-excited means who is supplying current to the field winding? Armature.
Yes, sir.
Armature, when it will supply? When there is voltage in armature.
Yes, sir.
When there is in voltage in armature, when there is some flux. Otherwise, how voltage will come?
Like I am supplying to the armature, sir. Like when at the time of on, I'm owning, and the time of on, there is no residual flux in the machine. But when I'm owning, some current will flow through the armature.
Okay.
So due to this current flowing in the armature, there will be a flux obviously developed by
Oh,
this
yeah.
thumb rule.
Flux armature current. If armature current is flowing, field winding there must be current. No?
Yes, obviously they will part away into field winding, and from field pole shoes also flux will come. Then these two
Yes.
flux can interact and.
Not clear your question. You are talking
Sir,
about shunt generator or series generator.
shunt, sir.
In case of shunt, if there is no residual flux,
Yes, sir. At the time when I'm starting, there's no residual flux. I'm giving input to the armature. That is, I'm giving a supply voltage V.
that is motor case, no?
Oh, correct, sir.
Yes.
Okay, sir.
Oh.
I didn't think of that. And sir, one more thing, sir. Last thing is regarding those 5 sets of problem you said that is important. Sir, in that, so generalized procedure is like to understand that only 2 things are needed. One is that EG equation is equal to n times phi.
Yes.
And another thing is to understand the initial condition of where in which direction phi resultant is
That
existing.
reference required. Otherwise, how can we judge directly?
Yes, sir. So
That's
only
why
these two conditions.
this way is the easiest way. You can easily answer the question. Okay.
Yes, sir. So based on these 2 equations alone, any type of this model can.
Yes. Any modification, apply in the equations, you will get the answer.
All right, sir. Thank you, sir.
Okay.
Sir, in first problem, sir, after the conditions are applied, the 12 volt becomes 0 volt.
Page number.
I didn't know the page number, sir. Sir,
I think where it is. This one, no?
yes, sir. Sir, here they said without connecting the field winding, there will be some voltage, sir. Without connecting the field winding, how there will be the voltage, sir?
See. Wait. Suppose field winding not connected. Okay.
Yes, sir.
Now you are rotating generator. Okay.
Okay, sir.
Now residual flux is there or not?
Yes, sir. That's only not connected, no, sir. Residual flux lies
Not,
with.
that's why I given 2 figures every time. These 2 figures is important like that. If it is even not connected also, no problem, because poles are there here. In the poles, flux is going, no? Residual flux, even there is no current, it is going. When you rotate, it will cut the flux lines, EMF will induce or not?
Yes, sir.
That is only 12 volts.
So then it means residual flux present in poles also.
Yes.
From poles also the residual flux. Am I right, sir?
Between poles only residual flux is there, no?
Okay. That's it. Thank you.
Okay.
Hello, sir.
Tell.
Good evening, sir.
Good evening.
Sir, that residual magnetism, that's a property in DC machine. Is there applicable for the induction generator where we are using only single excited, no, sir? Is it required that?
But there the RMF required, na, rotating field. That
Yes,
is
sir,
not DC excitation. So there we are using alternating rotating magnetic field. For that you need 3-phase supply only.
I'm asking induction generator, sir.
Induction only. Induction generator, what is the field we are giving? Rotating magnetic field, no? That is rotating at synchronous speed. That is not
Yes, sir.
possible no, with residual flux. Residual flux means maybe poles are fixed, there it can. But alternating field, we cannot produce residual.
Yes, sir.
That's why.
Sir, in universal motor,
Hmm.
we have having two types, no, sir. One is AC and DC type.
That is AC we can give, DC also we can give. That is universal.
We can use both types, AC and DC.
Oh, yes.
Sir, in our home, we are using universal motor as a AC motor, no, sir.
Hmm.
Where that use, sir, the DC motor means universal
DC.
DC motor.
Whatever in mixers we have, that is universal motor only. Like generally we are giving AC to that. But if you have DC battery, na, so try to
Yes,
give
sir.
and check it will run or not. Batteries. If you heavy batteries, any battery is there, you try to give that. It will work for DC supply also.
Okay, sir. Sir, at that time, that residual mechanism condition must be certified. No, sir,
Not
for the-
required. For motors, not condition, no conditions. But only for generators, we are discussing this.
Sir.
Okay. For motors, you
okay.
no need any condition.
Okay, sir.
Okay.
I got it. Thank you so much, sir.
Okay.
Hello, sir.
Tell Manikanta.
Good evening, sir.
Good evening.
In transformers, we are
Hmm.
using statically induced EMF, sir.
Hmm.
Flux is time varying.
Hmm.
But in DC emissions,
Hmm.
we are using dynamically induced EMF.
Hmm.
But we are EMF calculation అప్పుడు మనం ఎందుకు సార్ ఈక్వల్ టు d5/dt అని వేస్తున్నాం కదా సార్. అది స్టాటికల్ ఇండ్యూస్డ్ ఈఎంఎఫ్. డైనమికల్ ఇండ్యూస్డ్ ఈఎంఎఫ్ అంటే ఈక్వల్ టు బిఎల్వి సైన్ థీటా.
బిఎల్వి సైన్ థీటానే, కాకపోతే మనం ఇక్కడ రేట్ ఆఫ్ చేంజ్ ఆఫ్ ఫ్లక్స్ అవుతుంది కదా, అకార్డింగ్ టు దట్ వీఆర్ కన్సిడరింగ్. అర్థమైందా? అంటే
రేట్
మనం
ఆఫ్ చేంజ్ ఆఫ్ ఫ్లక్స్ ఇన్ టర్మ్స్ ఆఫ్ కండక్టర్ రొటేషన్ లో అవుతుంది కదా సార్.
అదే వీఆర్
కానీ
కన్సిడరింగ్.
మనం కంటిన్యూస్ గా ఇస్తుంది డీసీనే కదా సార్.
That is DC only. So anyway, you can derive using BLV sin theta. That is also correct. And we are considering one conductor, single conductor with variation of flux for one rotation. Okay, అలానే తీసుకోవచ్చు, no problem.
మరి అలాంటప్పుడు రెండు ఈఎంఎఫ్లు ఎందుకు సార్ మనకి? డీసీలో అయితే బిఎల్వి సైన్ థీటా అని, ఏసీలో అయితే d5/dt అని.
సో ఎనీథింగ్ యూ కెన్ యూజ్. అండ్ ఈ ఈక్వేషన్ ఎలా వస్తుంది? డైరెక్ట్లీ బిఎల్వి సైన్ థీటా అది డైరెక్ట్లీగా వస్తుందా? అది కూడా ఫారడేస్ లా నుంచి రావాలి కదా.
అంటే రెండింటికి రిలేషన్ ఏమైనా ఉందా సార్?
దెర్ ఈస్ రిలేషన్. జనరల్లీ మనం ట్రాన్స్ఫార్మర్ లో బిఎల్వి సైన్ థీటా యూజ్ చేయం డైరెక్ట్, ఎందుకంటే అక్కడ వెలాసిటీ ఆఫ్ కండక్టర్ ఏమి ఉండదు కదా. But in generators flow, there is a conductor is rotating in one generator and other generator flux is rotating. And anyhow మనం relative variation తీసుకుంటున్నాం, కానీ ట్రాన్స్ఫార్మర్ లో that is not possible.
Another doubt, sir. In transformers, we are giving DC supply, the transformer winding is burned out. But in DC missions, we are giving DC supply, the winding field winding is not burned out.
The field winding is having high resistance in case of field windings. Even if you give DC supply, current is not very high current. Current is limited kada ikkada. అర్థమైనా? But transformer winding resistance is less than 1 ohm, very low resistance. That's why they are burning. But not here because it is limited.
Yes, sir.
Okay.
Okay.
Any more?
Sir, could you explain that last point, sir? The AC and DC.
ACL?
He asked, no, sir, if you give the AC to the winding, it's not burn your signal, sir. Could you explain that?
Not AC. In transformer, we are giving DC. If you give DC supply, we said that it will burn.
Yeah,
it will burn because their resistance of transformer winding is what? Less than 1 ohm.
Okay.
Okay, but whatever field windings in synchronous machines are here, whatever the field resistance we are using, that is high values. like 20 ohm, 30 ohm, 100 ohms, 150 ohms, 200 ohms, in that range. That's why the current is limited in this. It won't go high values. Even we give DC. Satish.
Hello, sir.
Tell me.
Sir, in 15F, sir. We have said that with respect to characteristics, no, sir. Sir, what if, can you tell it practically, sir? What if we give the risk in shunt field, sir?
What?
What happens practically, sir, there if you go on increasing the resistance?
So if you keep on increasing resistance, no, suppose if resistance of field winding is very high, what is the ISH1 value?
Very low, sir.
VG1 by RSH.
Yes, sir.
Whenever RSH is very high value, what is the field current? Very, very less, almost zero.
Yes, sir.
Then due to that, is any flux will produce properly? No flux. That's why it cannot build voltage.
Okay,
That's why the resistance should be minimum, such that some flux should increase, build up. That's why we taken this.
Okay, sir. Okay, sir. Thank you, sir.
Good night, all of you.
Hello, sir.
Hello.
Sir, in transformers, low resistance, high inductive nature, na, sir.
Low inductance.
Low resistance, winding is low resistance and high inductive, na, sir.
Yes.
If DC is given after some time, at steady state, it can be short circuit.
So here, don't apply the transient analysis in case of these windings in transformers or DC. That is not applicable because there is an opposition here. That is we are considering, no? EMF induced according to Lenz's law.
Yes, sir.
Okay. So according to that, we will consider, but not like network theory transient analysis here. Okay. Good night.